Okay, welcome back, guys. This is probably the last video on 5.2 and 5.3 for this chapter. Last example, I think we worked on how to apply the binomial probability formula. And then in this example, we're going to use the technology part, how to get bypass using the binomial probability formula multiple times, like this one here. Right. So in this example, we're going to see that, especially for a procedure that involve a really large fixed number of trials. So suppose we are tossing a coin 20 times. So in this 20 coin toss trials, we want to figure out the chance of getting exactly 15 heads out of 20 toss. So n in this case is 20. X is getting 15 heads out of 20. P is the probability of getting one head in a single coin toss. That's 50%. And then Q is getting a tail in a single toss, also 50%, 0.5. So we want to figure out the probability of X equal to 15, meaning that is 20 choose 15 times 0.5 to the 15 times 0.5 to the 5. So this is using the binomial probability formula. Type that into your calculator. I'm going to do that one more time here. So you can see, actually, let's do 20, math, PRB, and choose R, 15 times 0.5, raise it to the 15 times, let's slow down a little bit. Let's delete, delete. What happened there? To 15, so we want to delete that one. Close parenthesis times 0.5, raise it to the 5th powers. Delete. Okay, so that should give us 0.014. So round that to about 0.015. So about 1.5%. So roughly 0.15. So that's the chance of getting exactly 15 heads when we do a 20 coin toss. So it's not pretty high. It's about 1.5%. Meaning if you were to go conduct an experiment of tossing a coin 20 times, the chance of you getting 15 heads out of 20 is pretty dang low. That's unlikely because it's under 5%, right? In this case here is less than 5%, so that's unlikely, right? All right, so now part B is worded a little differently. It said that what would be the probability of getting at least 15 heads out of 20 coin toss trials. Okay, so this means what is the probability of getting exactly 15 heads or 16 heads or 17 or 18, 19, 20. So we're going to have to rephrase this as the probability of X greater than or equal to 15. We're looking at the probability of getting 15 heads or more. So we have to add all of these probability here. 17, 18, 19, 20. So we have to add all these probability of getting exactly 15 or 16 or 17 or 18 or 19 or 20 heads out of 20 coin toss. So we have to use the binomial probability formula 6 times. So that's a lot of work. So instead, we are going to use the complement rule. We said, let's go ahead and take the 1 minus the probability of getting less than 15 heads out of 20 toss. Okay, so getting less than 15 heads out of 20 toss, you can have up to 14 heads, right? So you can say that is 1 minus the probability of getting 0 heads up to 14 heads. So that's what this event is simplifying to is less than 15 means 0 up to 14, possibly again 14 heads out of 20 toss, but you have to add them up because it's less than 15. It's not just 14, that's it, because less than 15, meaning you can have 0 or 1 or 2 or 3 all the way up to 14. All right, so now we're going to introduce the new command. So this probability, this sum here, this is called the binom CDF. Okay, and binom CDF, we can do 20.5 for P and then up to 14. Okay, so if we do this, we should get 1 minus. Okay, so I'm going to go ahead and take a minute and explain what this is on the side. So binom CDF of NPX. Okay, this is the cumulative distribution frequency. This gives us the sum of probability up to x. Okay, whatever the x here is. So in this case 14, so we're going to add the sum up to 14 from 0 to 14. So to access to that, you go to stat, you go to calculator, you go to stats button, and then you're going to go to calc, and you're going to go down to, actually no, it's going to be under distributions. You can do second, and then distribution will be the vars button here. Go down to binom CDF, okay, and then binom CDF, number of trials, you do 20 first, and then you do 0.5 for success, 1 trial, and then you do 14, meaning the sum up to 14. So that gives us that, okay, and then we then take 1 minus that, so you do 1 minus that right there. So that gives us about 0.02069. So let's do 0.9793. So 0.9793. Subtract that, so you 0.0206. 207. There you go. So to toss a coin 20 times, and the chance of getting at least 15 heads or more, our 20 coin toss is about 2%, right? So it's still unlikely. So in this case, it's still unlikely, right? Still unlikely. Okay. So that's using binom CDF, and I'm going to show you how to do part A here using binom PDF. Okay, so we use technology. We want to say this here can be done using binom PDF, binomial probability distribution frequency. So that is NP X. Okay, so in this case, to compute the exact probability of getting 15 heads out of 20 toss, we can type in binom PDF. It's not CDF, it's PDF of 20.5, and then in this case it would be 15. Okay, so we're going to type that into a calculator, and that should give us the same answer. So second, vars, which brings up the distribution. You go down to option A, binom PDF. So we do 20 coin toss, 0.5 for each toss, and then 15 heads. So that gives us about 0.147. So 0.147, which round up to 0.015. So all right, so same answer. So you can actually go back and use binom PDF for all these answers here to check the answer if you don't want to use the formula over and over again. Okay, and the last thing we discuss in this page here on this section is the parameters for binomial probability distributions. So if we have a probability distribution that is binomial, find the mean, variance, and standard deviation is really easy. Remember from the 5.1 when we introduced probability distribution, the mean, variance, and deviation for that is a little more complicated, but using technology is really easy. The formula is a little different, but once we look at a special probability distribution, which is binomial, that has 2 possible outcomes and all the other conditions, the formula is really straightforward here. Okay, the mean is n times p, variance is np Q, and then standard deviation is just the square root of that. So the standard deviation is the square root of NPQ. So really easy formula to remember. But let's go through this example here. So this is saying that, as mentioned in the previous section, that probability distributions describe the analogous version of the population. So describe the population. So therefore, the mean, variance, and standard deviations are considered parameters, not statistics. Okay. And the mean can be computed as n times p, right? So another word for the mean from the previous section, we understood the mean is the same as the expected value, same as the expected value, right? So in the homework, sometimes problem might might ask you to find the expected value, but it's not saying the mean. But really, it's asking you first to find the mean of that distribution, that probability distribution. It may word it in a way where, find the expected value of getting number of, how many number of heads from certain, coin toss trial. I don't know. Or, when we guess over here, when we're looking at guessing, the question right here, where is it at? Actually, I'm going to show you how to do that this problem. In example 7 is kind of a good way to demonstrate what the expected value would be. So let's get to that. If we have a surprise true-false quiz with 12 questions and the students are unprepared, okay, then all their answers can be guesses, okay? Find the mean and the standard deviation for the number of correct answers by guessing for each student, okay? So we're saying that the mean is mu equal to n times p. In this case, n is 12. P is true or false, so it's 50% guessing. Q is also 50%. So the mean is 12 times 0.5, which equal to 6. So we're saying that the mean is 6. In other words, is the students are expected to guess 6 questions right out of 12. Okay, so if I have a class of 40 students and the students are unprepared for this quiz and each question is true or false, I'm expect to see the average of question that gets correct out of 40 students is around 12 questions, right? And that's what the expected value, but that's what the mean is really referring to in a binomial or in a probability distribution, is the expected value to be approaching if we look at a larger scale. Okay, find the standard deviation. So the standard deviation will be sigma equal to the square root of npq, which is the square root of 12 times 0.5 times 0.5, and that gives us roughly 1.732. Okay. Part B is asking, would it be unusual or significantly high for a student to pass by guessing 10 correct answers? Why not? This asks us to use the range rule of thumb again, so let's go ahead and get to that. We need to look at the minimum usual score or questions correct. So minimum usual questions correct. And then we look at the max usual questions correct, right? So from the range rule of thumb, we're looking at mu minus 2 sigma for the minimum value and mu plus 2 sigma for the maximum value. So that's the mean is 6 minus 2 times 1.732. Down here is 6 plus 2 times 1.732. So 2.536 and 9.9464. Those would be the boundary for separating the unusual and the unusual value is high or the non-usual value at all. So in this case, to answer this question, would it be unusual for a student to pass by guessing 10 correction correct? The answer is yes. So we'll say yes, it is unusual. Unusual for a student to guess 10 right, because it is more than 2 standard deviation above the mean. Okay. Part C, is it unlikely for a student to guess at least 10 questions correct? Okay. So this is asking, how likely or for a student to guess 10 questions or more correct out of 12, we're looking at 80% or higher here. Is that unlikely? The answer is going to be yes. To answer this, we have to look at the probability of guessing at least 10 correct answers. So this is asking for the probability of x greater than or equal to 10. Okay, out of 12, that means we're looking at x10 plus x11, guessing x12 mean question right. We want to look at this sum of probability here. Is this less than or equal to 0.5? Is this unlikely to obtain? So that's unlikely. Okay, well, let's find out. Okay, so what we can do here is we can do 1 minus the probability of x less than 10 using the complement rule, and that is 1 minus the probability of guessing 0 question right, guessing 1 question right, all the way up to 9 question right, because it's less than 10, right? But we don't have to do this for all 9 times using the formula. We can just go ahead and use the binomial CDF of 12 question, 0.5 for each question, and then up to 9, and then that should give us 0.192. that is less than 5%. So we will say that yes, it is unlikely. Okay, let's check that really quick. 1 minus second vars binomial CDF 0.5 and then up to 9. So the sum of probability of guessing up to 9 questions correct, subtract from 1, so that give us this is not correct. What did I do wrong here? Binomial CDF, oh, that's not 20 but 12. I think I did that wrong. 12 questions, 12.5 and then 9, so that gives us about 2%. So that's less than 5%, therefore it's unlikely. Okay, there's a couple of examples that would be more fun for us to do if we were to do this class, if we were taking this class in person. So there's a lot of fun stuff here, but I'm gonna go ahead and stop on this example, give you a chance to just kind of soak through this and do some homework questions and then ask more questions on Zoom.